Hello, in this video, I'm going to demonstrate to you two things. One is using Wireshark, the other one is how the Wireshark application Wireshark is basically an application that monitors the interface traffic, network traffic received on the interface, and then it presents to the user, such as us, in a readable format. We can do some packet analysis, network analytics using Wireshark. So in addition to that, we want to learn how Wireshark basically captures the packets on the interface in binary format, decodes it, and displays it to the user. So we want to understand how we will do that kind of decoding. So that will be useful for us in the future if you want to do some packet analytics. We can write our own code. We can capture the data that is received on the interface, and then we can decode those. And if we want to do some network analysis, we can do that. So the first thing I will do is, as you have all installed Wireshark, I will start up Wireshark. Okay, so here let it start. So we are able to see here there are four. For me, there are four interfaces. This is the interfaces we want to start a capture on. So we have the Wi-Fi interface. We have the loopback interface, and that loopback is basically any messages that are or packets that are being sent within the device. Let's say two processes want to communicate with each other. They can also do like within the device. So that is that is loopback interface for that. And then we have the Ethernet interface, which is not connected. I also have an VPN software installed, so it has a virtual interface. So we are able to see here that the Wi-Fi interface is having some traffic. So this is the interface that we will monitor, and it has a certain IP address. So this interface is assigned an IP address, and also the IP address, there are two types. One is IPv4 address, the other one is an IPv6 address. The IPv4 address is 10.1.17.30 for my Wi-Fi interface. So let us start a capture. So we can just double click here, or there is an option for here, start capturing packets. So just double click here. So the packet data that is being captured, it is now being captured. We can stop the capture here. So these are the list of packets. So each packet, the time duration starts from 0. So we are starting packet number. Anyway, we start capture. This packet number is from 1. Time start from the start of capture. So now this is displaying a few properties. So the data that it captures is binary, and now it's decoding that and it's displaying the IP details. What is the source IP? What is the destination IP for this packet? What is the protocol for the packet? What is the length of the packet as a whole? So it is the entire binary packet. So we will go into the details. So the entire binary packet here, it is mentioned to be 80 bytes on the wire. It's not on the wire, it's on Wi-Fi. But if it was on the wire, it would be 80 bytes as well. And then there is the Ethernet layer, which is also 80 bytes. Basically, that's the Ethernet frame. And then on top of that, we have the IP protocol, we have the UDP protocol, and then this is the DNS packet. So this is the one selected packet. And so we have, on top of UDP, we have the DNS protocol. So Ethernet is basically, so the physical layer is the bits that are sent by the Wi-Fi device. And then on data link layer, that is the Ethernet frame. So at the physical layer, we are sending some bits. It has some additional fields within that. So it will do some error correction. Within that, we have the Ethernet frame, which is the data for the physical layer. So the Ethernet frame, let us see for this packet, we are seeing there is a source IP address, a destination IP address, and it's a query to classroom.google.com. So basically, we're trying to find what is the IP address of classroom.google.com. This is what the packet is trying to do. And it is getting, also it is, the next packet is querying for HTTPS version of classroom.google.com. It will get a response here. So you see there's a standard query, there's a standard response, and there's the address requested is classroom.google, and the IP address response is 142.250.205.46. So it's making a request to which server? So this is the IP address of my Wi-Fi interface. It is making the request to another machine, that is a DNS server. Okay, so let me show you how we can observe the IP address of our machine and some other network configuration. So we'll go to the terminal. Here we can write ipconfig/all. So for the wireless LAN adapter, that is Wi-Fi, we have our physical address. So what is the physical address? This is the MAC address of the device. And the first 3 bytes are reserved for the vendor. So here the vendor is Intel. And the last 3 bytes are reserved for the device address. So multiple vendor IDs can be assigned to Intel. It's not that a specific 3 bytes because there are not so many vendors. Anyway, so there we have that. So this is the IP address that is assigned to the Wi-Fi interface. This is the network configuration that the interface that is configured, and then there is a subnet mask 255 to 55 to 55.0. So this tells me that the network address is 10.1.17.0, and so basically it is 10.1.17.0 slash 24, right? So 32 bits is the IP address, and so slash 24 tells that the first 24 bits or the first 3 bytes of the IP address, that is 10.1.17, represent the network address, and the last byte or the last 8 bits represent the host address. So anyway, so the default gateway is basically the router on the network. As you can see, it is on the network. So 10.1.17, same network address, and it is the last IP on the network. So the first IP on the network 10.1.17 is 10.1.17.1. The last IP is 10.1.17.254, which is the IP address of the router. So any packets that are being sent within this network, they will be sent directly to the device. If it has to be forwarded to some other network, such as the public internet, it has to be forwarded to the router, which is the default gateway here. So DHCP server, it's on a different network, but it is used to configure the network settings. This configuration, whenever the device starts, this configuration is provided by the DHCP server, which we discussed in the class. And then we have DNS servers, domain name system servers. So they will basically given a name of the website or a domain name, it will return the IP address. So here we have local DNS servers within the campus, and these are the IP addresses. So we made the first packet here was actually a DNS query for classroom.google.com. So here the source IP address is my own IP address, and the destination is 192.168.168.1. So the DNS server. So we are querying the system is querying classroom.google.com IP address. So all communication has to happen over IP addresses. Domain names are for our convenience, so we want to find what is the IP address of this website. So that is being sent to the DNS server, and we will get a response here. So the response came as 142.250.205.46. So this is the IP address. Now we can communicate with Google Classroom. Okay, so the Ethernet is disconnected. So anyways, that's it. So this is how, so what is happening is we have done a long capture, so I'll stop the capture. The next thing we want to do is we observe this DNS query. Okay, let us go through the in-depth what is the 3 panes. So the first pane here is the list of packets. Here we have in the second pane here we have the protocols in each layer. And here we have the packet bytes, binary format. So here is the hexadecimal format, and here it is being displayed as bytes. So some of them are readable, some of them are not readable because it's a binary packet. So the first packet starts with the Ethernet frame. As you can see, the Ethernet frame is this. So if I select the Ethernet frame, the first few bytes are the Ethernet frame. So it starts with the destination MAC address. So this is, what is the destination MAC address? Destination MAC address, so the IP address is 192.168.168.1. Its MAC address is 8C44A55E219F in hexadecimal, written in colon separated format. So these bytes, just 8C44A5, just they are written in colon separated format. So this is the destination MAC address. Source MAC address is the MAC address of this machine, which can be seen here, C858 going to B3, C858 going to B3. So the first 6 bytes, these are the destination MAC address. The second 6 bytes are the source MAC address. This machine, this Wi-Fi interface. The next 2 bytes are the type of packet or type of protocol that is inside the Ethernet frame. So after the destination, source, and type is the data part of the Ethernet frame. So this specifies the type of the protocol that is coming inside Ethernet frame. So here 0800 in hex represents the IPv4 protocol. So now we'll go to the IP packet. So in IP packet we have, so here this is where the Ethernet frame ends. So after that the IP packet header starts. So in IP packet header, the first 4 bits, that is the 4500, the first 4 bits is 4, that is representing the version of the internet protocol. Here it is 4. Next is the internet header length, that is 5. here 5 tells how many number of 4 bytes are there. So it is 5. So 5 into 4, 20 bytes. That is the size of the IP header. Then we have differentiated service field. So this is related to congestion control for IP. And then there are fields for total length of the IP packet. So this will tell what is the size of the data portion of the IP packet. The identification of this specific packet, each IP packet will have a unique identification, which will help it in case. So what happens is a IP packet may have to be fragmented when it is transmitted over a network, and then it has to be defragmented again, joined back together. We split it in case the network does not support packets of this size, and then we join it back together. So in case it is to be fragmented, these flags will be used. So this identification will uniquely identify the packet which has been fragmented in case. And then there is a fragment flags, which in this case mentions that it is don't fragment. So this packet should not be fragmented, and the fragment offset is 0. Time to live, this field tells that how many hops, after how many hops this packet should be dropped. So 128 hops. At each router, this field will be decremented. After 128 hops, in case this packet goes in a loop, it will be dropped. But this packet is just going to the next destination, which is 192.168. So we are on 10.1.17 network, so it will go to the default gateway. The default gateway will decrement the time to live field, and then eventually it will reach the destination, which is again a DNS server. So it won't cross the hop limit. This is too high. The hop limit to anywhere on the internet is usually within 20. So unless there is a special, like the packet enters a loop due to some routing issues, it will never be dropped because of this. One of the ways that the people analyze so what happens is whenever a packet is dropped, the router will notify the sender that it has dropped the packet. There is a program called trace route, which starts with time to live 1, 2, 3. So at each router, the packet is dropped, and the router, at each point in the path, the router will drop the packet one by one, and then the application, which is trace route, will be able to trace the hops that the packet is making on its way to a given destination. So that is one of the applications of this field. So now we are in the IP header. So Ethernet frame, IP header. Here we have the protocol. So again, protocol is the next. So we started with version, IP version, the header length, the flags, the length of the packet, one after the other. So identification, there is another. So there's a differentiated service flags. This is IP flags. Then there's time to live, 80 in hexadecimal. So that is 128 in decimal. Protocol 17 tells that it is a UDP packet. So Ethernet frame is data link layer, IP is network layer, UDP is transport layer. And then we have the checksum for the IP packet, which here is mentioned that it has not been validated. Next is the source IP address, 4 bytes. Next is the destination IP address. And then we have the IP data. So this is where the IP header ends, and we will have the UDP header next. So Ethernet frame, IP protocol. So the IP protocol mentions that in the protocol field, the next protocol is UDP. So the next protocol UDP has, so it distinguishes two things. So it has a source port and a destination port. So on an interface, there can be multiple applications communicating between two systems. So to distinguish between applications, we have port numbers at the transport layer. The source port here is a random port, and for DNS protocol, port number 53 is used. The DNS server is running on port 53. The length of the UDP packet is 46 bytes. That is the data part of the UDP. So the entire UDP packet is 46 bytes. The UDP payload is 38 bytes. There's a checksum, again, which is unverified because, again, IP header already has a checksum, but this is the structure of the packet. And there is the UDP payload. So now we have the transport layer. Now in the application layer, we have the domain name system, DNS protocol. So here we have some flags for the DNS protocol. It is indicating that it is a standard query. It contains one question, the address, what is the address of classroom.google.com, and okay, so that is the query, and then we have a response. So we observed so we have this binary packet. This is how the Wireshark decodes it. You want to decode it, we have to understand what is the structure of the packet, and we'll be able to do the same. So now here we are observing the bytes of the packet. Let us go and observe the packet diagram. We go to edit, preferences, layout. So for the third pane, we will use packet diagram. Okay. So again, here we observe the destination. So basically the packet diagram is telling that one line of the packet diagram represents 32 bits, or basically 4 bytes. So the first 6 bits are the destination MAC address. The next 6 bits are the source MAC address, and the next 2 bytes represent the type of the protocol inside the Ethernet frame. Here it is IPv4. Inside, so next after this Ethernet frame is the payload of the Ethernet frame. So within the payload, the next protocol is IPv4. Inside IPv4, here is the header. We have the version field, which is 4 bits or half a byte. Next half a byte is header length, which here is 5, which tells that 5 into 4 bytes is the header length. So the IP header length is 20. Differentiated service field, this is 8 bytes. Sorry, 8 bits, 1 byte. 2 bytes which specify the total length. So there is one thing that we want to note here. All computers use little endian format for storing numbers. On the network, all network devices use a big endian format. So what happens is in little endian format, the first lowermost 8 bits, least significant bits are stored the first. Higher significant bits are stored in a higher offset. In big endian format, it is the reverse. Higher is basically how we do it in decimal notation. So we write 100. So the 1 represents the higher significant digit, most significant digit. So here the most significant digit in big endian format will come first. The least significant byte or digit will come at the last. So that is how we can decode the total length field. So again, there's the total length field. Then we have the identification of the IP protocol, the flags, which will tell whether to fragment or not. What is the fragment offset in case it has been fragmented? Since it has not been, it is 0. Time to live, which is 128 protocol. Inside the IP data, the protocol is UDP, and then there's a header checksum, which is here 0 and is unverified. And then we have the source IP address. The destination IP address is the DNS server. Then we have the IP data, IP payload. Inside the IP payload, the protocol mentions is UDP. So UDP starts with the source port. This is our source port. Destination port is the port number of the application specific port number, which is here is DNS. For DNS, the port number is 53. The length of the UDP packet is 46. The size of the payload is 38 bytes. The checksum is the checksum of the UDP packet. Inside the UDP payload, we have the DNS packet, which is in application layer. UDP is transport layer, IP is network layer, and Ethernet is data link layer. Okay, it's both long Helani. So now we have a packet capture. What is that we want to do next? So this is how you start a capture. This is how you stop a capture. If you want to restart the current capture, this is how you do it. This is any capture options. Okay, so if you want to start capturing on some other interface, this is where you can do it. Next is we have done the packet diagram. We want to add a column called delta. So what we will do is there is a class. 1 minute. Classroom. Okay, so the next thing we want to do is we want to add a delta time column. Okay, so what is happening here is we have the time each packet is received from the start of the capture. And so we want to measure what is the time gap between the two captures. For example, here we are seeing like the time gap is around like 773 microseconds. And there's a big time gap here. So two packets have been sent rapidly. Then there is a big gap. So basically, this is a separate packet. And then there is a response is coming in around 4 milliseconds to this request. So anyway, so basically what we want to do is we want to see the time gap between contiguous packets, one after the other. What is the time gap? So time delta. For this, we will do edit. We'll go to edit, preferences. Here we will go to, okay, we did this packet format, right? So the first thing we will do is we will go back to packet bytes. Then now we will go to columns. We want to add a column called delta. So this is a new column. Let's call it delta. And the type will be delta time displayed. Okay, so here the column has been added. Let me drag it close to time. So, okay, so here it is easy to see, like the time gap between these packets is quite low. This is how we'll add a new column. Now, if you want to remove it, remove this column. Clear, easy. Next thing, what you want to do is basically you want to measure something. Okay, so you don't want to measure. We want to do a coloring rule. Okay, so we want to try out what is a coloring rule. So as you can see, all packets here, there is no colors, only the selected packet is being highlighted. Some packets, like this TCP packet, if there is a duplicate packet being sent, the Wireshark is highlighting it for us. Some other packets are being highlighted in different format. For example, this is a basic connection close, TCP connection close. It is being highlighted in gray. So we want to create our own coloring rule to highlight the packets. TC, TLS, TLS is basically HTTPS data, secure communication data, and this is also highlighted very slightly. I'm able to see it, just very light highlight, different color. So we will do our own coloring rule. We'll start here, let's say. Anyway. Okay. So go here, view, coloring rules. Here we want to do a coloring rule. So we already have a coloring rule for connection closure. TCP SYN FIN. So basically, SYN is like making a request to connect as well as making a request to close the connection. Basically, it is testing the server. TCP reset is a disconnect immediately. TCP fin is a simple connection closure. TCP request reset is an abrupt connection closure. We want to observe connection requests on TCP, so we will add a coloring rule. So it will be TCP dot flags dot syn equals 1, double equals 1. Let us call it TCP syn. We can make the background light green and done. So let us see if there are any packets highlighted in green. So here, right. So this is a TCP connection request. So my PC is making a connection request to this destination. Connection request, syn is a connection request. Synac, the server is responding with Synac. So basically it wants to connect back and is acknowledging that it received the connection request. And finally, we are acknowledging that we received its connection request as well. So both make a connection request and there is a connection. Acknowledgement for both connection request has been received at both ends, then there is a connection. After that, there is a TLS packet. It's an encrypted packet between this, it seems to be for Office apps, live.com. So this is highlighted. Now what we want to do is we want to filter packets that are the same, right? We want to we want to find only packets that are connection oriented packets. So that is TCP flags syn double equals 1. So we filtered only connection related packets, TCP connection related packets. So we're connecting with this server. We're connecting with, where is the other server? This is another server. 52.109.56.3 is the first server. 23, 52, 40, 90 is the second server we're connecting with. All of the connection requests that we made during the capture. To clear the filter, you can clear it here. Now we had to type the filter if there is some particular filter you want to use repeatedly. Okay, let's do another filter. We can filter out HTTP packets. This is the HTTP packet filter. We can filter out DNS packets. Okay, so another filter is, let's say, frame contains. So if a particular frame, Ethernet frame, contains, let's say, baby tree. So there is no frame that contains baby tree in the capture. Anyway, so what we'll do, if we want to make a shortcut for the filter, we'll add the shortcut here. TCP syn. Display filter is tcp.flags.syn double equals 1. Okay. The shortcut is created, right? Now you want to remove the filter, just remove it. You want to remove this shortcut, done. Next thing we want to do is we want to, uh, yes, let us observe the HTTP filter. So let me, okay, so there are some packets in the HTTP filter. Okay, let me try to connect, let me try to find any frames that are connecting to YouTube. Frame contains YouTube. So none of the Ethernet frames contain YouTube. Let me start the capture, continue without saving, and let me try to open YouTube. Okay, so the reason it didn't come because YouTube is a secure website. It uses HTTPS, so everything is encrypted. And at least the DNS query we should be able to see, but YouTube DNS query did not need to be made because we already know. The system already knows the IP address. It has been opened recently. So what we'll do, we will open a site that has not been opened recently, such as, let me go to the list of sites that I sent, HTTP sites. Mm, where is it? This is here. Okay, so this is the list of sites. Let us try, let's say, this one. Copy link, and let me open it here. Not working. Huh? Let me try babytree.com. Okay, so this is an HTTP site, not secure. So we should be able to see a baby tree. Okay, so let's go to Wireshark. Frame contains baby tree. What? Okay, why is it not coming again? Frame contains. So I guess I opened it recently again, so I need to open a different site. But anyway, let me click some page. Okay. Open.babytree default. Should come, right? Okay, let me open a different site. That way we will be able to get the DNS request. So the list of sites is here. Let's go to this one. SNEA India, not secure. SNEA India. Okay, let's filter for SNEA India. Frame contains SNEA India. Okay. SNEA India. Okay. .com. No, not coming. Why is it not coming? Stop the capture. Restart the capture. Continue without saving. Frame contains SNEA India. Okay. Why is it not coming? So because I'm capturing on loopback traffic capture, that is the issue. Okay, let me stop the capture. Done. So I will capture from the Wi-Fi interface, right? So frame contains, it's a baby tree. Okay, there's no such frame. Now we'll go to baby tree. Okay, refresh the page. Okay, so we are seeing some packets from baby tree. So this is the DNS request made, and we're getting another request for HTTPS, and then we are getting a response. This is the IP address of baby tree. So we are able to filter packets that contain baby tree. We can also have our SNEA India, none. We'll go here. Okay, so we got packets for SNEA India. Happy Independence Day. Next thing what we want to do is we created a filter where the frame contains certain bytes. The next thing we will try to do is, okay, try to observe a conversation, right? So we want to observe a conversation between two parties. So for that, let us say you want to track the conversation between us, which is 10, 1, 17, 30, and 142, 251, 223. So prepare as filter conversation filter. Okay, so we can directly go to conversation filter IPv4. Done. So IP address equals 142.251.223 and IP address equals 10.1.17.30, either of these. So this is the conversation happening between the servers. It started with some encrypted payload. So it is a quick protocol which is HTTP 3, HTTP version 3, and it is protected, and it happens on top of UDP, which is why we can see here in this packet, quick protocol is the application layer protocol which uses UDP as a transport layer. And another interesting thing is, for this packet, the request is coming from our IP address. The destination is the server. The port number that it uses is essentially the same port number as HTTPS, but it is a UDP packet. And so basically, it is a better version of HTTP. Quick is a better version of HTTP which supports multiple streams on like on a particular port number. Okay, so for now we are able to filter this. We are able to do this. So basically, we are able to filter this. If you want to change, so and is basically we can do the same as and equals is the same thing, equals. Let's say we want to do and it should be quick, or is there anything else you want to say? Let's say uh, frame dot len greater than, or let's say less than 80. So frame length less than 80 is being filtered. Okay, so this done. Next, what we want to do is, let's see. Okay, so one thing, if you notice here, the source IP address. So one thing we want to notice here that the source IP address, destination IP address is given. So one thing we note here is that for this particular packet, let's say, the destination MAC address is our own MAC address, and the source MAC address, it is the MAC address of the default gateway. So now, if we want to be able to tell like which vendor made this device, we can resolve the MAC address. For this, we'll go to Edit, Preferences, Name Resolution, Resolve MAC addresses. Okay. So as you can see, we now have our own MAC address, which is C858 going to B3. This is an Intel device. The router, the default gateway, is 8C44 going to 9F. That is a Cisco device. The way it is able to tell this is based on the first 3 bytes, which tells the vendor ID. So now we know which devices the communication is happening between. Now we want to resolve the IP addresses as well. Again, let's go to Edit, Preferences. Here we go to Name Resolution, Resolve Transport Names. Okay, so one thing we want to do is resolve. Let us see what Resolve Transport Names does. So let's go to remove the filter, Edit, Preferences, Name Resolution, Resolve Transport Names, Apply. So now, one minute. What the filter, what the name resolution is doing is, so we did edit preferences, name resolution, we resolved the transport names. So what that is doing for us, the AT port number in the transport layer, the AT port, so there are port number, source port, destination port. The first 1024 port numbers are reserved for, like it is reserved port numbers for different higher level protocols. So HTTP is a higher level protocol. It is on the application layer. So 80 protocol is reserved for HTTP. 443 is reserved for HTTPS. For DNS, it is 53 as we see. So this is what the transport name that has been resolved for 80 is demonstrating. Now we want to also resolve these IP addresses. So you're just seeing numbers here. This is my own IP address. This is the IP address of some remote server. Let us do resolve network IP addresses. So here we will resolve it based on the DNS packet data that has already been captured in this session. So if there are any names, any queries, for that query, let's say classroom.google.com, there was a response. From the response, we came to know what is the IP address of classroom.google.com. So the Wireshark will use that information to decode or resolve the names of these IP addresses. The other thing that is possible is for Wireshark to do a DNS query in case it does not know the name of the IP address. So for now, let us go ahead with within the capture IP address. So Wireshark will try to decode it. Okay. So these packets, right? It is going to font Google static, G static, again SNEA India that we opened. Now this IP address, it is not known. So this is what we can do because it is not involved in the current capture. I stop the current capture. Go to edit, preferences, name resolution, and we will allow Wireshark to do DNS requests in order to identify what is the name for the IP address. Okay, so it resolved the IP address. As you can see, now we have a name for this HKG07S50INF4 dot. So it is some internal website. So then we'll go. So we now know resolving the IP addresses. Next, we want to do. Let's see, geolocation. Let's do geolocation. So first thing we'll do statistics. So resolved addresses. So all of the addresses. So basically FFFF. So this is for the MAC addresses. This is MAC address. Oh, so the first one is an IP address. This is a broadcast MAC address. This is the Cisco router. One of these is so the first 3 bytes. Right? First 3 bytes tells it is a Cisco router, and this is the Cisco gateway. The first 3 bytes is telling this is Intel in the MAC address, and this is the MAC address of my device, an Intel device with the following device address. For these IP addresses, these are the names that were resolved. All of the names are here. Close. Okay. So now we'll go to statistics. Anything interesting here? Let us go to endpoints. So on IPv4, all the communication happened between these devices. This is my IP address. The packets sent are 10,000 packets. Communication is happening with the following endpoints, the following IP addresses. As you see, we know the following information. We know the address. We know the packets sent, the bytes, transmitted packets, received packets. Now we want to do name resolution. It is enabled, so we are able to resolve the names. There's some package to GitHub, baby tree, Opera, because I'm using this browser. And next what we'll do, we will go to, okay, so now what we want to do is we want to do geolocation. We want to identify where this server is located. For this, we'll go to edit, preferences, name resolution, and here we have enable IP geolocation. So for this, what you need to do is you need to go to this classroom. Here I have given a zip file which is in the first lab record instructions. You can download this, open a new window, download. Done. Okay, I have already downloaded it towards that. So delete this one. This contains 3 databases. For a given IP address, it will identify the first database will identify the autonomous system number. The second one is for city. The third one is for country. These files, I have copied them to a folder here. These are the files. These are needed for geolocation. So I'll go to max find in edit preferences name resolution. I'll go to max find database directories. Add a directory here, dconfig max find. Okay, and then you can enable geolocation. Okay. So now, not only we have the names of these servers. If you go to IPv4, the destination. So what is the source? For this particular packet, the destination address is our system. The source address is a some device. So let us see the destination address is okay, but the source address is Google. So it's the Google server. It's in the US. It has ASN number 15169. So Google network, Google autonomous system number is 15169. If we go to some other packet, let's say this one again, this one is also from Google. Let's say we go to SNEA India. So here the source IP address, this is the source SNEA India server, is in India, IN. ASN number is 17439. It is the name of the autonomous system is Entity Communications India Network Service. Where is it located? It is located, let's see, the latitude longitude is given here. So in order to simplify this, we'll go to statistics, endpoints, IP, all the servers we communicated with. Okay, so here we have more detailed information. Let us do name resolution. Okay, and then here we have for SNEA India. It is located in India, but the city is not known. For others, Chennai is known for this particular ad website, it seems. And then there is a Pune server, a server in Pune. Its name is not known, but it is known that it is in Pune. There's a server from Singapore, and the baby tree is in Beijing, China. So now we can go to map, open in browser. Okay, so these are the servers we communicated with several servers in US in 3 different locations, or we can zoom it further. Okay, so there's a location here as well. And servers in India, the servers in China. Okay, so there is a server in India, so many of them. This is Microsoft Corporation. Okay, this is again Microsoft. This is Akamai. This is Akamai International. Okay, this is a Singapore server. Akamai. Okay, the communication is happening between Akamai, different places. In China, this is ChinaNet. This is Beijing, I think. Beijing. Huawei Cloud Service Data Center. This is the Baby Tree website in Beijing. There's a packet to Europe as well. Amsterdam, Opera. Okay, Opera is in Netherlands. And then we have a packet here. Which place is this? Canada? Toronto, Canada. So there's Google in Toronto, Canada. There is Opera in US as well. Okay. Opera servers in US. So many servers at this location. I think it's all Google. It's all Google. Anyway, so these two are Fastly. Okay, that's a CDN. Again, a CDN. Okay. So interesting. What else in India? So it is Akamai, right? Okay, right. What is this one? Entity Communications. So that is this SNEA India website. That is server is here. Okay, done. So now you're able to find the locations. Huh? Okay, let me go ahead and close this.